Now it's time for Renato's lecture number 3.
Okay, thanks. So before I start with the thermodynamics, let me make a very small review of what we did and also an outlook of what we are going to do. So essentially my 4 lectures are split into 2 halves, as you may have seen, which are not very closely connected. The first half was about essentially the nature of quantum theory, where we tried to find out whether quantum theory is in some way a unique theory or whether there may be alternative theories. And the other part is about thermodynamics. So of course, both topics which are, one could call foundations. One is foundations of quantum theory and the other foundations of thermodynamics. So just to very briefly review what we did, and I also want to use that opportunity to give you a chance to ask questions if something was unclear during the last 2 lectures, because I think I just made it to the theorem, but then we didn't have much time to discuss it. So what we showed, or what I showed you without giving a proof, is a type of theorem as they are currently done by several people in this area at the intersection between quantum information and foundations, where one tries to make statements about quantum theory within the space or kind of considering other alternative theories. And what we have shown is that any theory that is compatible with quantum theory, in other words, any theory that is compatible with what we observe in current experiments, which is complete. So any complete theory must be equivalent to quantum theory, provided one additional assumption holds. And this additional assumption was this freedom of choice assumption. So in other words, we kind of gave, or I kind of gave a justification why we consider quantum theory and why we don't only see it as a historical particularity that may be different when we look for other things. So now, one important thing that I didn't say is that I don't want this result to be understood as a no-go theorem. So it shouldn't tell you that now we shouldn't look for any alternative theory. That's not the purpose of this thing. I think the purpose of these theorems is to just show where the boundaries are. So if you now want to have a theory that goes beyond quantum theory, what the theorem tells you is that you have to go beyond one of the postulates or assumptions that we had. So one of them was, of course, that we are compatible with quantum theory. So either you can hope that we find something, maybe experimentally, that contradicts current quantum theory, but that's maybe more something that the experimentalists are looking for. But you may also give up the other assumption. I mean, there are only these 2 assumptions, compatibility with quantum theory and freedom of choice. The completeness is kind of clear. That's not really an assumption. It's just in order to make a sensible statement, you assume that you have a theory that cannot be, that already includes everything you have. So the other assumption is the freedom of choice assumption. And I'm not claiming that this is an assumption that necessarily has to hold for any theory we will find in the future. But the theorem tells you that if you want to go beyond quantum theory, then you have to drop these assumptions. And maybe you find a different notion of free choice if you want to keep freedom of choice in some way. Or one may argue that this is something that is simply not needed, something we made up. But of course, current theories all have that. Classical mechanics is an example. I always make this example. If I want to calculate in classical mechanics what happens if I drop this piece of chalk, then I can freely choose somehow from which altitude I drop it. And freely choose doesn't mean, I mean, the assumption doesn't mean that I have some randomness in my brain. It's just a statement about the theory. The theory doesn't constrain me. The theory allows me to calculate what happens if I drop it from here or what happens if I drop it from here. And the same is, of course, for quantum theories. Quantum theory allows me to choose the parameters differently. And one may even say that something is not really a theory if I don't have this freedom. But the freedom of choice was kind of defined in a special way with respect to this chronological structure. And there is certainly room to weaken that in some way and still have something reasonable. So this is just to stress the fact that I don't kind of claim that this is a no-go theorem. It's more like something that shows you it would immediately tell you that if you, for example, have a theory that satisfies the assumption, if I give that as an exercise, please come up with an alternative theory. And I would see that the theory satisfies the assumptions, then I would immediately see that the theory cannot be different from quantum theory. It would be in one-to-one relation, even if it was maybe formulated with respect to other mathematical objects. So that's what we did. Yes, you have a question.
Another popular option to drop the assumption about the specific chronological structure that you assign to the...
Yes, that's what I meant. So when I say that we somehow drop this freedom of choice assumption, of course this freedom of choice assumption mathematically is an assumption about probability distributions, which at the end it's about certain independence of certain variables. That's what it is. And in order to formulate it, we introduced this chronological structure. And so if you change that structure, for example, if you say that somehow there is not this time ordering that is relevant, there's something else, then this may result in a different assumption and the theorem may no longer hold. So it's the full assumption that, of course, I meant now, and I said this is the constraint we have. So I'm not saying that if someone comes up with an alternative of what freedom of choice means, then the theorem, of course, doesn't necessarily hold. The freedom of choice, as I introduced it, is the one, as I mentioned, motivated by Bell, or actually introduced by Bell in one of his articles. And if you think about it, I mean, this is an interesting maybe task, which is not in the problem set. But if you, it's an interesting problem to think about an alternative way to define what freedom of choice means. I mean, freedom in the sense of you want to capture the fact that we can kind of make choices, that the theory allows you to make choices at random. And I haven't seen so far any alternative definition that is somehow consistent with itself in some way. But yes. But of course the structure should still make sense in some way. Yes, I agree with that, Yes, I agree. Okay, there's another question there.
I don't really I understood it formally, but I don't really see the interpretation. Especially you said that, for example, I would get the implication that the adversary in a QKD protocol can't trick me by having additional knowledge or things like that. And I don't see how this comes out. For example, I'm thinking about theory now, in which actually I have non-locality, for example. That's a simple example. So you can have a wave function, or you could have a special wave function, which carries a little wormhole between the two endpoints where we do the measurements, and instead of collapsing the wave function, it just communicates one measurement to the other place and tricks me that way. And then I really have secure QKD in that setting. But still, it doesn't violate the two assumptions you make. So it seems that, so I don't really understand.
Okay, that's a very good question. I didn't go into the details of that. I also don't now want to go into the details, but I nevertheless would like to maybe give you a hint on how the answer looks like. So it's right that if, for example, an extended theory would include something like a force or something we don't see now. Like if I, for example, look at something here, then immediately, instantaneously, this is somehow broadcast to everywhere else. And maybe I simply didn't notice that in current theory. That may happen. Now, the reason why this is not, I mean, of course you can argue what now security means, but at least the way security is usually defined, this is not the problem, surprisingly. And why is it not the problem? Of course, it's completely insecure, but what you prove in cryptography, and the standard approach is exactly what I now tell you, is that you somehow consider what people call an ideal functionality. So, for example, for quantum key distribution, the ideal functionality is something like a box that gives a key out to, let's say, Alice, and the same key out to Bob, and the key is completely uniformly distributed, and nothing goes to Eve. So here would be Alice, and here Bob, and nothing goes to Eve. And then what you say is that you have now an actual quantum key distribution protocol with wires and stuff, and then Alice does something and gets also a key, and SA, and Bob gets a key SP. And then what you show, or what you actually define as secure, is if the behavior, if you put that into a box of this whole thing, is the same as the behavior of this ideal resource. And the same in a strong sense. So even everything that adversary can do here, he can also do here. Now, the point is that if you had something like superluminal signal, or an additional force, or something, a broadcasting mechanism that just happens and we don't notice it, then this could also happen here.
Say that which, so for example, if I measure,
Yes.
so I make a photon pair, if I measure one of the
Mhm.
photons, this will actually turn the other photon. So I make special photon pairs which allow superluminal communication. That does not mean that everything is radiated out of my lamp. It's just that what the effect what I do on that photon goes to the other photon.
Yes.
Or it could be, it doesn't even have to be superluminal communication. I just don't see, this is just one example I can
Yes.
come up with. I don't see how
I mean,
this function
okay, there are some. I mean, you have to make, of course, certain assumptions, but one assumption you make is that it shouldn't be relevant on which information carrier you represent your information, for example. And so, for this ideal system, you would say, let's assume I get here the key and represent it on an arbitrary physical system. And if it is now the case that certain physical systems have the property that they immediately broadcast everything to the adversary, then already this ideal setting, you have the broadcasting of information. And so the two settings are still equivalent. So in some way, a cryptographer would say, it's still true that everything you reach in the ideal world is, or everything you reach in the real world, or any attack that is possible in the real world is also possible in the ideal world. But you're absolutely right that I have to be careful with defining this, because of course I could still use here a different type of system, as I say, a specially prepared photon, which I don't use in the ideal world, because I mean, it's not clear what I use here. And then, of course, this argument doesn't apply. Someone has to define all the things in such a way that this is excluded. Someone has to be careful and take that into account. But the idea is roughly that if there is such a strange thing happening that you're describing, then I somehow consider that thing also happening in the ideal world. And then I still have the statement that the real world is somehow equivalent to the ideal world. So somehow in a world where there is no privacy before, I mean, I know that you have a different example in mind, but just to illustrate this thing, in a world where there's no privacy because everything is immediately broadcast, then this thing is still by definition the ideal resource. It's just a very useless one. And so I still, according to the definition, reach that. So the point, maybe the short version of the answer, and I'm happy to discuss more details later, is that security doesn't necessarily mean secrecy in a cryptographic sense. So I didn't claim that you have secrecy, because there could just be a theory in which we don't have any secrecy, but we would still have the equivalence. But this is maybe a more technical discussion. But you could also, an alternative is to do the following, to say that let's just still make certain assumptions, like that we can keep things isolated if we want. And then you don't need these considerations. Then you can even make the claim that it's actually secret under this assumption, of course. So the assumption would then say that any theory that goes beyond quantum theory, but where the isolations we have are still isolations with respect to the additional forces and everything we discover, then it's still true. So, but these are different ways of maybe expressing the same thing. But the main point maybe of the statement is that assuming, I mean, we had this additional lambda, and we had here the wave function. The point is that whatever this lambda is, we don't learn anything more than the wave function. So in particular, if the adversary had access to lambda, it doesn't learn more. But of course, the lambda still has to satisfy the assumptions of the theorem. And actually, if you think about the assumptions, they already imply certain things. For example, they imply that a certain type of non-signaling is also valid for this lambda. So that's another part of the answer. But that is a very good point. One has to be very careful about these statements. And if you're interested, I can later show you how they are made in more detail. Yes?
Alternative theory, isn't it something like instantaneous, like where the time evolution comes in?
Okay. Yes. So I didn't, in all I said yesterday, I didn't talk about time evolution, which doesn't mean that I don't consider theories in which we have time evolution. It's just that I don't need to make the time evolution explicit. So I only need to know certain aspects of the theory in order to make statements. So in other words, when I had this diagram, maybe you remember I had this thing that I said we make here a choice C, and then later we make certain measurements. And then we have here X and here Y. Now and there's some parameter lambda. Now if you go to this alternative theory, then of course to compute the probability distribution of these outcomes, you may need to do something that corresponds to time evolution. So at the end, what I said, what you need is a law which is formulated in terms of a probability distribution. So the law should tell you, depending on the choices you make, what is the probability distribution of the outcomes. And so in order to specify that law, for example, in quantum theory, you of course may need to include the unitary evolution that the particle undergoes when it travels from here to here. I was just talking on an abstract level where I said, let's just assume we already have that here. And then I didn't need to talk explicitly about how you calculate this probability distribution. So everything about evolution and so on is part of the rule of how you come up with that. So just as an example, if I now replace lambda by the wave function psi, and I consider the wave function I have here at the source, and here is some unitary evolution, then this thing here is of course given by the Born rule, which includes the evolution. So I would write something like that. I had these projectors here, AX, tensor P. I mean, these are the two measurement projectors of the two measurements. And then instead of here writing psi, I would write U psi, and here I should write U dagger psi. So this would all be included in this distribution. So I didn't talk about it because it's kind of, we don't need to know exactly how this comes about, but this doesn't mean that there's no evolution in the alternative theory. Of course there is. It's just that we didn't need to make it explicit. Okay. Okay, if there is no other question, then I would like to go on with the new topic. So the new topic is, maybe I should also say something about the problem sets, because I had two problems in the problem sets about this topic. However, the problems were both referring to the proof, which I thought I may be able to present, but I didn't have time to do so. Nevertheless, these problem sets are interesting, but to see maybe the motivation behind them, you may, after solving them, want to have, or even before, have a look at the actual proof. The proof is not hard to read now, as you know all the concepts. The proof is maybe one column in a PRL-style paper, and you find the proof on, as I said, there is this paper that I just managed to put on the archive. So if you now go to the archive and go to new submissions, then you find a paper explaining the full proof, and you can look at that, and then you also see why the problems are posed in that particular way. So in case you're interested, look at that. You may also just only read the proof without the problem sets, of course. So it should be easy to understand now as you have all the concepts. Okay, this was about the problem sets. Now let's move on to thermodynamics. So one thing we are going to prove in thermodynamics is that erasing things, like erasing this blackboard, requires a lot of work. And we will make that more precise. But let me give a more general introduction first. So as you have seen last time, I always like to have tables and compare things. So we have, I would like in this case to compare thermodynamics with information theory and make connections between them. And of course, when I write here information theory, I mean information theory in a general sense, including quantum information theory, but not restricting to quantum stuff. So certain things may be said already on a classical level. Now, of course, these are two very different things. And if you think about what is the operational motivation to even consider these theories, then they're very different ones. So traditionally, thermodynamics has been introduced a few hundred years ago when people started to study engines, like, for example, steam engines. And this was kind of, lots of thermodynamics was developed in the context of the development of such technological, of new technologies related to that. For example, also, of course, things like fridges. And maybe as a counterpart, people also use thermodynamics to, for example, look at black holes. It's, of course, something very different from a fridge, but you see, thermodynamics has a very broad range of applications. Information theory is, of course, traditionally been developed in order to look at settings such as communication. Also, this is two-party scenario, but also one-party scenarios such as, for example, data compression. So you want to communication, for example, over noisy channels. You have an optical fiber, and you want to know how much data can I send per second over this optical channel, or how many movies can I store on a DVD with a certain capacity. So these are very different goals that the two series had, and also let's say the quantities that we are considering are very different ones. So in thermodynamics, there are things like temperature, and maybe also, okay, as examples, heat and work, and maybe efficiencies of engines. And in information theory, what are the corresponding quantities? You can easily think, you probably know that well. For example, we are interested in channel capacities. That's exactly the thing that I said. How much information can we send? Or compression rates. So these are again very different things. However, if you now look at the mathematical tools, they're also actually very different. So we have also quantities here, such as the entropy. And maybe you remember from your thermodynamics classes that in thermodynamics, entropy is usually introduced in such a way that you have somehow a differential way of defining it, that the increase of the entropy is given by the heat. Q would be the heat you supply to a system divided by the temperature. And in information theory, we have a very different quantity, however, with the same name, so let me call that thermodynamic TD, the S information theory, which is, for example, in the case of quantum information, defined like that. And of course, there is also, I don't now talk about statistical mechanics, but of course, statistical mechanics is somehow in between in the sense that you're talking about such things, but use an entropy which is defined in that way. But I will now kind of look at thermodynamics as an extreme case where you don't look at microscopic things, and information theory as something where you have somehow, the traditional or the usual definition of entropy that we use. Now, there is, so in some way, you could say that if you think, what are the common features? Why do we even want to establish a link between the two? Because what I said so far is actually they are very different. So one of the common features of these two series is that they're both series about objects about which we only have limited information. So when we talk about the steam engine, we talk about just a few parameters of the engine and don't want to take into account the microscopic details. They're not even modeled usually in thermodynamics. So we don't want to talk about the position of gas molecules. So in some way we want to, starting from very limited information, make statements about useful statements that are operationally relevant. And this is also true here. We have limited information. For example, we only know a probability distribution about certain data and want to make statements about that. So, but the other striking similarity is that both of them use entropies. Now you could say this is cheating because entropy is defined in a very different way, but at least there must be a reason why there is, in both cases, we call this object here entropy. And just as a historic fact, let me mention a statement that von Neumann made when he was suggesting to Claude Shannon a name for this. At the beginning, this was just some uncertainty measure. Of course, Shannon introduced it for classical probability distribution. And so he was looking for a name, and what von Neumann said to Shannon is the following. He said that you should call it entropy for two reasons. And so he gave these two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name. So that's, of course, a good reason. In the second place, and more important, no one exactly knows what entropy really is. So in a debate, you will always have an advantage. So that was the reason why it's also called entropy. And so let's now see whether we can make somehow a stronger connection and maybe even try to understand what entropy means. So apparently at that time, no one understood it. So let's see whether we can go beyond that. At least information theory is a theory where this is a central object. So we should hope that we can understand a little bit more. So what are the questions that we are trying to answer today, or today and tomorrow? so first of all, we want, so this is kind of a motivation for the whole two lectures. So first of all, it's of course the general question, which will kind of be implicit to everything we do. How are these two theories related? And we will see that there are strong relations. I mean, quantitative relations. So I will not remain on this philosophical level. We'll actually be able to take statements from here and translate them into statements here, and also vice versa. So that's kind of a general goal. But we will also have certain specific goals, which illustrate what I want to do here. So, for example, we could ask ourselves, can we solve possibly open problems in thermodynamics, such as problems related to thermalization? I will explain later what that exactly is. But roughly it's the question, why do systems thermalize? Why do they reach some thermal equilibrium? And there are many people working on that. There are many explanations. And we could hope that or also classical information theory, but in particular quantum information theory, gives us some more insight on why thermalization happens. And we will here also have quantitative results using information theory. But we will also go in the other direction. So that would more be use something from information theory to thermodynamics. But we could, of course, also do the other thing and ask ourselves, are there things in information theory that we want to know where it's useful to use thermodynamics? And of course, there are many such things and very practical things. For example, we want to know what is the thermodynamic cost of information theoretic operations or of information processing. So what I mean by that is something very specific. So the question more precise is that you have now in technical terms, for example, a trace preserving completely positive map, F. So this is just the most general mapping you could have, and you could think of it as this models any information processing that you may possibly want to do. For example, very simple things, such as the erasure of information. This is, of course, a very trivial map, but also more complicated things like a logical gate, like an AND gate, or a whole circuit, or even what a black hole does. That's, of course, also from an information theoretic point of view, you could say this is just some map. And now the question is, what is, how much energy or how much work do you need, at least, or do you need for an optimal implementation? Of course, you can always be wasteful, and then I don't know how wasteful you are. But if you do it optimally, there will be an answer. So there will be an explicit formula that takes as input the description of the mapping and tells you now how much work do you need. And that will be one of the quantitative connections that we will establish between these two things. Okay, so that's roughly the goal. And before I now start, I would like to mention certain, I would say, almost fundamental problems that we have if you are not careful, if you try to reach that goal. I mean, maybe they're not problems for you, and if they're not, that's of course a good sign. That means that you have already maybe the right view on these things. But if you take the wrong perspective, you have inherent problems. And why is that? So one problem is that you may have is the following. So some people think, oh, let me start from here. So how do we think of entropy in information theory? So in information theory, it's very natural to consider entropy as a quantity that expresses the knowledge we have about the system. And as that, it's somehow a subjective quantity. For example, if I toss a coin, this is not the coin, but I don't have one. So I toss a coin and don't show you what the outcome of the coin is. But I look at it. Now we can talk about the same object, the coin that I've tossed. Now, the entropy that I would assign to that is 0, because I looked what the outcome was. So I have no uncertainty about it. If I now ask you, what is the outcome of the coin toss, and how much certainty you have about it, you will probably answer 1. because it's a random bit, and which is probably equally distributed. So the entropy you assign to the coin that I've tossed and the entropy that I assign to the coin toss are different ones. And that's usually the way we use entropy in information theory. I mean, in a very natural way, we talk about even conditional entropies. We condition on the knowledge that, for example, in a two-party scenario, that Alice has about something and the knowledge that Bob has, and there are different quantities. Now, in thermodynamics, when we talk about an object, we usually talk about it as if the entropy was something, really a property of the object that is objective. So we talk about the entropy of a gas. Or some people, and that's something that maybe the organizers of the workshop can explain to me better, some people talk about the entropy of a black hole in a rather objective way. I mean, at least maybe they mean it's just the entropy they have about the black hole, but it sounds usually more objective if they talk about it as a property of the black hole. So in thermodynamics, it's kind of usual to talk about uncertainty or about entropy in an objective way. And this is also not unreasonable, because you could say that usually everyone has roughly the same knowledge about the devices. So if we talk about the steam engine, then we all agree that we don't know the position of the particles, but we know the temperature, maybe. And so in that sense, this works well. Nevertheless, this is a conceptual problem, as we want to establish rigorous relations between the two, because they're simply different objects. This is somehow an object that is well defined. It's even, if you look at the definition, it's how much heat you supply to the system. And you would think that heat is something very objective. If I put my hand onto a hot plate, then I burn it, so I can see that heat is something which is measurable. So how can it be that this objective thing is somehow related to this subjective object here? So that's one difficulty we are facing, but you will see this is not hard to overcome. Yes?
Can we, with this question and the relation between the two different entropy, somehow can we state in that way, like when we increase the heat without giving any information, like summer like heat, it doesn't mean it doesn't mean it has some information. There is no information. You can create.
Yes. Yes.
And then, but the other side, if you increase the entropy, somehow you have to change the information.
Yes, but I would say that, I mean, if you, for example, I mean, let me just make an example, and then it will probably become clearer what I mean by that. So, actually, the example that I would like to give is an example that I would also like to give, because I think some people ask me about this KTLN2 that Michał Hordetzky was talking about. He said that he could write papers without KTLN2 and then multiply the papers with that, and then he has a new paper. So let me briefly explain how this KTLN2 comes in, because it's actually very easy, but it's maybe good to do it once explicitly, and this will also connect to the example. So one thing that is, this fact that entropy should be something, at least from an information theoretic point of view, subjective, is of course well known and has been considered already in the early days of thermodynamics. So this is not a new insight. And in fact, it was Szilard who gave a first interesting example. And you have seen this Szilard engine already yesterday or before yesterday. So the Szilard engine is the following Gedankenexperiment, and actually it's maybe today no longer only a Gedankenexperiment, because people can now design single particle systems. Of course, not that type of engine, but similar ones with a similar functionality. And so the idea is that you have a one-particle gas, and then you somehow think about inserting a divider into this box. And then if you now have information about where the particle is, you may gain that information by measuring, by just looking where is the particle. You can use this box now to generate work. How do we do it? So one way that it's usually drawn is to say that we somehow connect here, and we have here a piston, and I now do it in a more complicated way than one has to, but you will see why later. I could connect here some weight. So here's some mass, which is very small, of course, because there's only one particle. And I also assume that there is some heat bath at temperature T. I will just explain you why this is needed. And now you see this particle will, of course, push against this piston. And, of course, it will lose energy by doing so because it will lift the weight, but it will constantly gain energy from the heat bath. So that heat bath makes sure that the average velocity of the particle is always the same. And then we can see how much energy we can gain out of that. And that is exactly KTln2. I mean, maybe I should even briefly make this calculation. So the calculation is usually done using the gas law. So the gas law for a single particle is that one. And now this is the pressure, this is the volume, this is the Boltzmann constant, and this is the temperature. This is just the gas law. So now the pressure is, of course, the force divided by the area, where this would be the area. So this would be the area of the piston, and this is the force. And the volume, I can write the volume in terms of, if I measure here x as where the piston is, then I can write the volume as x times a. And then the a cancels. So I have this formula here. So in other words, I have this formula, F times x is equal to kt. Now, how much work do I gain? So the amount of work I gain, the total energy, the work is, of course, given by the force times the length I'm doing. So it's the force, which depends on x, times dx. And now you can do the simple calculation. I should maybe say something about this box has maybe length L. So I start with L half. So I start here on the half position and do the integral until L. So here as well, L half to L. And now I insert this formula. So this is kt divided by x dx. And now if you see you get this KTln2 because kt is constant, because I assume that there is this thing is in contact with the thermal bath, and I do the process slowly so that it always is kept at the same temperature. And then I have here the integral of 1 over x dx of 1 half to 1 L, if you like. And this is ln2. So this is how the ln2 comes about. So the work you gain from this process is KTln2. Now this, I gave this example because in the problem set you will find another example which is more realistic in some way. I mean, it's very hard to maybe build a single particle engine. But what people can do today, and maybe you have seen that already, is that people can now very well design two-level systems. So you could imagine that you have a system with two states, and the two states are at a certain energy. And initially, they're maybe in the ground state. And now I could somehow say a Szilard engine corresponds in this scenario to a scenario where I have one state that is occupied. So this ball indicates that this state is occupied. And at the end, what I end up with is that, of course, at the end of the process, the particle will be in both halves with equal probability. So at the end, I still have a situation where with probability 1/2, the particle is here or here. And now you can ask yourself, is there a clever process to go from here to here, which allows me to draw work from this system? In the same way as here, I go from this situation to a situation where the particle is somewhere, and I draw work by this process. And the exercise that you can look at is a description of a kind of process that goes from here to here and allows you to gain exactly this amount of energy. And the idea is essentially that you raise and lower these energy levels in a clever way. So first you raise this energy level because it's empty, you can do it at no energy, and then you put the system into contact with a thermal bath and lower it slowly, and then when you do the calculation, which is all described in the problem set, you will find this formula. So this formula is kind of not constrained to a Szilard engine. It's actually valid, and that's also part of the statement that Landauer made. I will come to that later, that any system where you somehow use one bit of information to gain work will result in exactly this amount of work, KTln2. So indeed, we used here one bit of work, of information. We knew whether the particle is on the left, on the right, or on the right, and at the end of the day, we didn't know it any longer. But we have gained something, namely this amount of work. Okay, so that's the Szilard engine, and I will often use it. That's why I wanted to explain it explicitly. And that now explains where the KTLN2 comes from. But you should always keep in mind that KTLN2 is not something specific to the Szilard engine. It's really general, and that's why I have this problem set where you do it with another example. And more generally, there is this claim by Landauer that it's always like that.
So,
Yes?
so in this derivation, we have to assume that somehow you're adjusting the mass, so it always moves slowly, right?
Oh, yes. Actually, yes. So this is actually not so easy to implement. So one way to do it is indeed you would have to adapt the mass. You could also have some more clever mechanism with a spring or so. So actually, I'm not sure this would work because there are also fluctuations in the system and so on. So the claim here is not, I mean, one should be careful. I'm not claiming this actually works. What the more important claim will be that we cannot do better than that in some way. So we will never be able to get more work out of that. Actually, in reality, we try, because I was also curious about that, I tried to actually find an explicit mechanism to implement that. And then you have to think about how do you change the mass of this thing and stop the weight when it has reached its altitude, and do that even if you have fluctuations, because of course the velocity of the particle will fluctuate. And it turns out that this is very hard, so I didn't manage to do it. So I'm unsure whether the Szilard engine actually works if you take into account fluctuations. This is something that is probably easier in some way, but you're cheating a bit because this is a half-classical picture, because here you're talking about energy levels that you raise and lower. And so it's unclear whether you can do it at the precision you would need to do. So it's actually an open question whether you can really implement a one-particle Szilard engine. But for example, at ETH, we have a collaboration with experimentalists doing ion trap computing, where we try to demonstrate that this thing actually works. But it's unclear whether it will work. Of course, this is now a quantum language to describe it. But no, it's not coherent. It's always in a mixed state at any stage of the protocol. Yes, there was a question.
Pressure.
Yes.
Can we talk about pressure if we have single particle?
Yes, this is exactly related to the question before. So as I said, I was very skeptical, and I tried to simulate this whole thing, and it has so large fluctuations whenever you simulate it that I'm not sure it actually works. That's why I think this is actually a nicer model. And this is, by the way, I think Michał Horodecki mentioned that as well. This is something that has been proposed by him and I think Galitsky and others, this idea of, or maybe there was also work before, but at least they have a very nice description of that in their paper.
I would like just to understand what the statement is. You said this is actually true in general. That's why you're considering another example. And is it something? And then you mentioned it's also something that Landauer has
Yes,
asserted.
yes.
But what is the actual status? I mean, is it something that one can formulate and prove?
Yes, we will do that. So you have just to wait a bit. We will make a more precise statement about these processes. And this will hopefully answer the question. Otherwise, just complain if it doesn't. Okay. Now, what does this Szilard engine now have to do with this discussion about the engine? Because now we could go back and ask, what happens now with this Szilard engine if we look at thermodynamics? Because in thermodynamics, the entropy of the Szilard engine should somehow not depend on whether we now have knowledge of the particle or not. Someone in traditional thermodynamics would, of course, just say we don't know the particle position. But that's somehow not a very satisfying answer, because in principle we could measure it and still want to apply maybe thermodynamics. And it shouldn't be the case that now these things suddenly become subjective, but they will actually. And the reason is a very simple one. The reason is the following. So if you learn thermodynamics, then at some point in thermodynamics, at the very beginning usually of the course, one does the following. One says that one defines somehow the internal energy of a system. This is sometimes called U or E. So usually, at least in the German class, we call it U. I don't know why, actually. And then you decompose the internal energy. So you say the increase of internal energy of a system can be decomposed into an increase that is due to work and an increase that is due to the supply of heat. So the energy of some body, of some system, can increase because I heat it up, or because I, for example, apply some work, because, for example, by friction, or of course, friction depends on how you look at it. It's from outside, it's work, from inside, it's cube, but you could even compress a gas, for example, and that's work. And then with that, you will, of course, change the internal energy of the system, but you can also heat it by putting it on a hot plate. Now, I was always wondering, how do you actually make this distinction? And the point is that this distinction is really just a subjective distinction, and that's why, at the end, the entropy which is defined via delta Q is subjective. So what do I mean by that? Let's now go back to the Szilard engine to explain that. So in the Szilard engine, we could look at the following scenario, and that will now explain why I had this slightly complicated construction. I could still have this divider in the middle, and now let's have somehow a mechanism where I have two weights, one on this side, so they stand here on the floor, so they cannot be lowered any further. So this is one weight, and here is another weight, and it also stands on the floor. And now you could say this is a very clever mechanism, because I don't need to know whether the particle is on the left or on the right. In any case, if it's on the left, it will just push the piston in this direction and lift this weight here. So then I've gained work. And if it's on the right, it will lift this mass here. So in both cases, I've gained work. And of course, I didn't even have to know the particle. Now, what would one say to match that with what we know about thermodynamics? That it shouldn't be possible to just gain work out of a system which is hot. That would, of course, violate the second law of thermodynamics. So the point is, first of all, that if I know that the particle is here, then indeed, as I just showed, I can gain work. That's what I just showed. I mean, as I said, it's maybe hard to implement that, or maybe even because of fluctuations not possible, and you may have to do it in another way, but you can gain work. Now, what was the implicit definition of work that I used here? The implicit definition was that there's now a well-defined degree of freedom in which the energy is stored, namely this mass here. So the energy is now stored here. So in this sense, I've really gained work. Now for someone who doesn't know whether the particle is here or here, one of the two masses will be lifted. And now why should I consider that work? Actually, I shouldn't, because I don't now know whether the work is stored here or here. So that it's no longer true that the energy that I had in the system is now in a well-defined degree of freedom. It's either in this degree of freedom or in this one, but I don't know it. And that's exactly the situation I have in the first place somehow. So energy that is somehow distributed over many degrees of freedom, in this case only two because I have only a very simple system, but energy that is distributed over many degrees of freedom and I don't know exactly where it is, should be considered as heat. And so in this simple case you have energy, so if you don't know the position of the particle, the energy will be distributed over these two masses. Of course it will be in one of them somehow, but I don't know in which one. So from my point of view, it's still not work. It's not work in the sense that it's energy in one well-specified degree of freedom. And so you see, in this sense, heat is really a subjective quantity because the experiment would be exactly the same. Both experimenters, the one with knowledge of the particle and the one without, could use the same construction. Just the one with the knowledge will know at the end that the energy is here. So for him it's work, whereas the experimenter who didn't know doesn't know where the work is, and therefore would consider it as heat. Of course, you could now say he could look which weight was raised, but looking at it will also cost him work. We will see that later, so that doesn't work. Okay, there were some questions, I think, in the back. Yes? Sorry? I already answered it. That's great. Okay. So that explains now that shows that we don't run into this problem. So actually these quantities here that we have are not as objective as they appear. So the heat is somehow unordered energy, but unordered refers to our knowledge we have about the system. So for someone it could be ordered and for someone else not. So this means, by the way, that if I now burn my hand on a hot plate, this is not because of the heat in the plate. Because if I have sufficient knowledge about the plate, I would know the movement of all the particles precisely. Nevertheless, they would burn my hand because, of course, there's still a lot of energy in the plate. So whether I know whether this energy is ordered or not doesn't change anything in whether I burn my hand. So in this sense, this was not a counterexample. So the fact that in usual language you say we burn our hands because of the heat, this is just misleading. It's actually because of the energy. Whether it's work or heat doesn't really matter. So in this sense, the energy is, of course, a kind of objective thing, but this distinction between heat and work is not. And that we have to keep in mind. Otherwise, we will run into contradictions when we do the connection.
Could one say, if you knew the positions of all the particles, then you could have arranged your hand in such a way?
Yes, exactly, yes. I thought about saying that, but I had no clue about how to do that. So, yes. Then you could actually even draw energy and don't have to eat later because it
I think it's essentially that it's not burning you, it's punching you, but it still hurts.
yes, right, yes. You would probably describe it differently, right? That's right. Maybe the only objective thing is that it hurts. Okay. Or that your hand is at the end no longer there. Okay. So now we have a little bit of general preparation done. Now let me go a little bit into a direction which will also answer this question that was mentioned before about what did I really mean when I said that it's always this KTLN2. Oh, sorry, yes, sure.
The distinction is between whether you know or you don't know.
Yes.
Between whether you know the particle hit you or something else hit you. But
Yes. I mean, yes. So the distinction is whether you know that the particle will hit you exactly at that time in this location, or you just know there will be many particles that will hit you constantly, but you don't know where exactly.
Thermodynamics is very objective. In thermodynamics, it's very objective.
So yeah, I would say, but it's not an objective statement. So, yes. So what the distinction I want to make is that in one case we don't know how it hits us, and in the other case we do, but that will of course not have an impact on whether it hits us. But yes. Okay.
Well, couldn't you say, if you had control over all the atoms in your hand, then you could, you could
Yes.
imagine maneuvering them in such a way that they would always avoid these
Yes,
particles
exactly.
of the fire.
Yes, exactly. Or as I said, they could even try to gain the energy from the hot plate and use it in a useful way and put it into your blood and change maybe, kind of do some chemical process that will increase the sugar in your blood and so whatever.
I'm just less ambitious. I just want to avoid
You just want to avoid being burned, yes.
Yeah.
Okay. Okay. Now, as I said, now considering that, I still don't know what the entropy of a black hole is. So maybe Patrick or John can later tell me what they mean by that, because if it's now something subjective, but I'm sure they have an answer. But maybe we can discuss it later, unless you have a short answer now.
It's objective.
It's okay, that's good.
It's a maximal entropy.
Okay.
So the dimensionality of the Hilbert space is objective.
Okay, so it's actually a statement about the dimensionality of a Hilbert space. Okay, then okay, good. Now,
Well, shouldn't the entropy of a black hole be objective or subjective in the same sense as any other kind of entropy?
Yeah, so a black hole can be in
Objective or
a black hole can be in a pure state, and then
Right.
its von Neumann entropy is 0.
yes. So they're just counting dimensions and calling that entropy. So that's probably the answer. Okay. Now, as I said, what we are also going to do now, as we have seen this Szilard process, so you see, you can actually run this Szilard process backwards. Why should this be useful? Of course, it will cost you energy, so you could kind of compress the gas. So rather than, now let's again go to the simple construction without this part. So we could do the following. We could start with a situation where we have something like that. And the weight is lifted. And now, so we have energy in the weight, and now we let the weight fall down to, or do work on the piston, while it's, of course, losing its potential energy, compressing the gas. So we could go from this situation to that one. And that will cost us exactly this amount of work. So we invest KTLN2 to go from here to here. Now, on an information theoretic level, you could look at this thing as what one sometimes calls erasure of information. Because you could say, if you now, instead of this Szilard engine, just think more abstractly here of a value, which tells you whether the particle is on the left or on the right. So you have some value x, and it's maybe 0 if particle on the left, and 1 means it's on the right. I mean, or x is just some either 0 or 1. So it's just, you somehow could think of it, you encode the value of the random variable x into the physical position of the particle. And now, if you do this process, then you know at the end that x will be 0, because now the particle is on the left, which encodes a logical 0. So in other words, on a logical level, what you have done is to reset a memory. So in some way you could say this is a bit, a register for a bit, which you reset into 0. And so whenever I will, in the following, talk about erasure of information, I mean this. Because erasure could also mean something else. It could mean that you erase it and then put it back into some mixed state. So what I mean is actually resetting. So maybe resetting is actually the better expression, but for some historical reasons, people often call that erasure. So you see, actually, this shows now that erasure, at least if I do it in that way, costs work. Because if I go from here to here, then I need to do that. Now you could ask the question, and this is now about the generality of these claims, is there a more clever method? Can I find another mechanism in which I can erase a logical bit or reset it, but spend less energy than KTLN2? So here the work that I spend is KTLN2. And now, and this is, it's now a debate whether this is now a theorem or a postulate, but what one can say is that what Landauer said, or Landauer's principle, is exactly the statement that however you implement this process, it will always cost you that amount of work. Now, in some way, there were many arguments about what this principle now means. Is this a postulate? If you take it as a postulate, then you can somehow use it to derive the second law. If you already take the second law as given, then you can use the second law to derive this principle. And I will later tell you why, but roughly the idea is that if you could do it better than at this cost, so if you would require less work than that, then you could, of course, do that process. And then you could go back on a Szilard engine. And when you go back, of course, what you have just seen is that you gain KTLN2. So you would have a cyclic process which would, at the end, give you a net work gain. And this is forbidden by the second law. I will make that more precise because I jumped now over many steps. I said that if you have a process to erase a logical bit, then you go back using a Szilard engine, which is a physical process. So we need to make a better connection between these two to make these arguments more precise. But roughly speaking, it's a matter of definition of whether you call Landauer's principle a postulate and then say this is something that implies the second law, or whether you take the second law as given and then derive Landauer's principle as a consequence of the second law. There's no, I mean, you can do both ways, but in some way they are almost equivalent. But as I will just now explain, it's not so clear what Landauer's principle exactly means. You have to be more careful even. So why do we need to, yes?
But didn't you say that the Szilard engine, that would be the best you could do, but you doubt yourself that it's possible to do?
Yes, okay.
So can you
Yes.
use this still the same argument?
To do that argument, I would need to have a process which certainly works at that thing. And whether this is the Szilard engine or not is a different question. So what I only need to have some process that does it. And I think there are actually many examples of, I mean, given, for example, by Charlie Bennett in some of his works where he proposes, for example, mechanical processes that do that are different from the Szilard engine. But essentially, we don't have an experimental realization of a process that really does that. But what you could argue is that what we certainly know is that if you have many Szilard engines in parallel, we could operate them in parallel, and that solves the problem. Because you could say, instead of doing that just for 1 bit, let's do it for 10 to the 23 bits. Because if you have a mechanism to erase 1 bit, we should also be able to apply to 10 to the 23 bits. And then what we do is we have now many, let's say, Szilard boxes, and now we just turn them around. So we can, in each Szilard box, the particle will be on the left or on the right. And we can always, of course, turn the Szilard box around, in principle without any energy expenditure, so that at the end I have a situation with many Szilard engines where the particle is all on the left. Now I can just connect all these pistons with each other, and then I have a macroscopic gas, because if I do that 10 to the 23 times, then clearly I have an object where I know that it works. So in that sense, it's clear that it works for that purpose. I don't need a single particle Szilard engine. But it's a good question, because from what I said, this wasn't clear. So one really needs to actually repeat the process many times. I cannot do it in one cycle for one particle without knowing that there is a process doing that. But we certainly know that there are large engines like that. I mean, this is very easy to implement. Of course, what is hard is actually to turn the individual Szilard engines around, but there's no fundamental principle that tells us that this should be impossible.
First picture is more entropy than the next picture.
Sorry?
First picture is more like a particle in the full, moving in the whole.
Which picture you are talking?
The
top one. Ah.
Top one is more entropy.
Yes, here you have more entropy, yes. Here you have an entropy of, let's say, 1 more than here. 1 unit of entropy more. And the unit of entropy, you may measure it via K. I mean, usually there's actually but this is just a convention that here, this entropy in thermodynamics will usually have a dimension of, because it's multiplied by a Boltzmann constant from here. So here you would typically have a unit, which is the same unit as the Boltzmann constant. Okay. Now, why should we be careful with this Landauer principle? So imagine, I now just told you that we can erase, or Landauer said we cannot erase it better than that. But of course this is again, we have to be careful about making objective statements, because it could of course be that we have here a bit which we know is 1, and then we can of course put it into 0 by a reversible process. So this, of course, we just have to apply a not operation, which is of course reversible. So if someone tells you that the memory content is a 1, and your goal is to reset it into state 0, then in principle you don't need any work. Because, of course there is again an assumption about technological feasibility, but the assumption is that any reversible process can be done at no energy cost. This is just an assumption that I make, but it seems a reasonable assumption for physical reasons. Yes, otherwise it would probably not be reversible. So we wouldn't call. Okay, so now this is okay. Of course, this doesn't contradict that, because here the assumption was that we don't know the bit. But what does it in information theory mean that we don't know the bit? So in information theory, we would actually, rather than saying the bit is just either 0 or 1, want to assign a probability distribution, because usually we have, even if we have no information, we would assign a probability distribution, maybe a uniform one. So the more general question is maybe, let's assume that we have some probability distribution Px, and now, x is distributed according to that, and now we want to find a process that brings it into the state 0. And of course we can also do that, by the way, for x doesn't have to be a bit. We may ask the question in a more general way. And it turns out, and this is something we will show later, that in that case, it's an entropy that comes in. So in that case, the work will be kT ln2 times some entropy measure, and the entropy measure is one that has already been used by Mihar. It's the max entropy of the probability distribution x. And I will also explain you what that means, also what this epsilon means. Again, it was introduced, but I will give a slightly different approach to that. So there is some entropy measure. And this makes sense, because entropy measures uncertainty. So if we know what x is. It doesn't cost us any energy to do that. And if you don't know it at all, then it's uniform. And if px is uniform, it turns out that the entropy is as large as the number of bits. So for example, if you have 1 bit, it will just be 1, and therefore give this standard Landauer principle. So in other words, what this tells you is that the Landauer principle is somehow not really the minimum cost you need, because this can be smaller than 1 for a bit, or even general. So this can be smaller than 1. So it's not true that we cannot erase a memory at cost lower than that. But it's true if the memory is uniformly distributed, so in case we have no information about it. And so what we will actually do more generally is to say that in general it depends on the information we have about that. So the question is now, what is this information I have about it? So of course it will be relevant how much the mechanism that performs the process knows about that. So in general we will have here a machine. There's some machine here, a device D, that carries out the process. And in a more general language, and this is actually what we are going to prove, is that what is relevant is how much the machine knows. So the actual entropy is here a conditional entropy of x given d, where d is the knowledge that the machine has. So the more the machine knows about x, the more efficiently it can erase the bit x. So that's kind of an outlook of what we are going to do next time. But now, okay, this was a very long kind of overview, which was not very technical. Now we will switch gears and go into more technical things. But I hope what you should have learned up to now is that it's important in all these examples to take this point of view that information is always relative to, of course, an observer. So it's always the information that someone has about the system. And of course, we also have to ask ourselves whose information is important. And for example, for the erasure, it's of course the information that the device has is important to decide whether this is possible. If we know that this is a bit 0, but the device doesn't know it, then it will of course require more energy. That's clear. But let's now do all these things on a more quantitative level. And in order to do that, I will now, for the remaining half hour of today, or 20 minutes for today, completely leave thermodynamics because I have to introduce a tool, a technical tool that we are going to need repeatedly. And this tool is called decoupling. Probably you have already heard about it. It's a technique that is used relatively widely in quantum information theory. It has been developed, I think, in the group of Patrick by Frédéric Dupuis mostly. And in Zurich, we have further developed that thing. And so I guess I will now just explain you on, we are now going to this information theory side and just explain you what decoupling means, what that is, and why it's useful. Of course, I will make remarks that will show you how this connects to thermodynamics. Okay, so what is decoupling? This will only be a very brief introduction into it, and so, but I hope I will be able to give you the main essence of it. So this is just an abstract problem, which is the following. So you assume you have a system consisting of a certain number of qubits. Let's say this is a system consisting of n qubits. And we call this system A. And now assume that this system undergoes some unitary evolution, and you should think of a random unitary. And I will later tell you what exactly that means, a random unitary. It can mean different things. And there is a lot of progress has been made in understanding what that really means and what we can constrain it to. So we do that, and then, of course, after this unitary, we still have the system A, but it's now in a different state. And then what we're going to do is something very simple. We're just separating the system A, which consists of n qubits, into two parts, into a system A prime, which consists of k qubits, and into a system A prime prime, which consists of n minus k qubits, where k is an arbitrary number between 0 and n. in addition, we are considering something that I call a reference system. So this is called that R. This is here. And this reference system may somehow be correlated to A, or A may be correlated to R. Now I don't, during the whole process, I don't change anything with the reference system. The reference is just there as a reference, so it shouldn't change. So it's there to kind of see what happens with the correlations. And what I'm interested in is somehow in the correlations that remain in this system A prime between A prime and R. Was there a question? Or? Okay. If not, so the idea is essentially to do the following. So we only keep the system A prime, and we want to know, is this system A prime still correlated to R? So this we just ignore. This we put into a bin. So this is kind of put into a rubbish bin. So we only keep A prime. Yes?
How much entanglement is there between R and A in the beginning?
Yes, we will just come to that. So at the moment it's arbitrary. It's just some joint state between this and that. And we now exactly want, I mean, this is exactly, of course, the right question. Of course, whether this will still be correlated or not depends on how much correlation there is initially between A and R. And this is exactly what the theorems will tell us, or the theorems will tell us under which conditions on the correlations here do we expect that this is decorrelated from that. So the goal that we want, and so the goal is of the decoupling, that also explains the name, that if I call this state here that I have rho prime, so it's a state between A prime and R, and let's call the initial state rho. This is just the state before I start. It's a state of A and R. So what the goal is that rho prime, A prime, R is almost, and almost could be measured with a distance measure and some epsilon, equal to some rho prime A bar, sorry, I should write it like that, the identity of A prime divided by the dimension of A prime. So this is just a completely mixed state. Tensor rho R. Because I don't change rho R, it doesn't matter whether I write here rho R prime or rho R. So what I'm requiring is that after this process, the system A prime is completely mixed and completely uncorrelated to R, up to some distance epsilon. But I'm doing so, I mean, the process is a very simple one. I apply a unitary U and forget n minus k bits and only keep k bits. And now you can ask yourself, I mean, it's now a very well-defined question to ask, under which conditions do I have that? Of course, these conditions will involve U, and it will involve somehow this initial state. If I give you explicitly the state and explicitly U, you can just apply U to the state and then look whether you have reached this. But this is not the goal. The goal is to say something for a typical U.
It seems like you're conflating two things here, because one thing you could ask is that you just have rho A prime R equals rho A prime times rho R, and then another thing you can have is that A prime is maximally mixed.
Yes.
So here you assume that both of those
Yes.
things are happening?
Yes. Mm-hmm.
Okay, so you really want both to be happening? Or
yes, yes, yes. There is a reason, actually, this question is a very good one, and there is a generalization of the whole concept, where I don't here just consider tracing. I mean, here what I do, the operation I do from here to here is just tracing out A prime prime. And more generally, I could ask the question, what happens if I here apply an arbitrarily completely positive map? And in this case, it's also not necessarily useful to ask here, what do I have here, the maximally mixed state? But in the case where I do a tracing, this is the natural thing to ask. But and one reason for it is that you will certainly have that whenever you have the decoupling, because what it somehow means, I mean, you could see it in the following way, that, of course, because you apply random unitary, the whole thing will be rather mixed anyway. And so if you had now I mean, the question is how much of your information you have about the initial state do you already include in R? So what you could say is that let's just randomly do a random unitary in addition to that one, to that, and include the knowledge which random unitary we did into R. That's something you can do formally. But this is operationally equivalent, because then you know what the state of this system is. But if you start with that one, then it's already automatically, without this additional process, completely mixed. So the complete mixedness of that is somehow a consequence of the whole thing. So the important thing is really the decoupling.
For example, if A prime was much bigger than both A double prime and R, and the system was in a pure state, then you would not have A prime.
Yes, yes. So, but as I said, I could always formulate it in an equivalent way with a different R, which would tell me which state I have, so that this formulation again makes sense. But you're right. I mean, you're absolutely correct that these are somehow, I could in principle separate the two requirements. And there are generalizations in which I actually separate them. But for the purpose we have now, we don't want to separate them. So, yes? Mm-hmm. Mm-hmm. Yeah. So let me maybe formulate now a theorem, and then maybe you see which question the theorem answers, because I don't want to write down the question formally, but just the statement we can make. And then we can come back to the question. So there's now a so-called decoupling theorem. And as I said, the first version, I mean, there have been many, and this has been an increasing or continuous development. And I think originally the ideas of that date back to a paper by Horodecki, Oppenheim, and Winter, where they did state merging. And I think they also say that the idea even goes back more to some other paper, which I think is not in quantum information. Maybe Patrick, you know that. But apparently there is something earlier on which their idea is based. Anyway, so this has a long tradition. And there is increasingly, let's say, more precise statements. And I will now give you a statement which is somehow in the middle of the development. There are more general statements, as I said, the ones where this trace is replaced. And this is actually needed, the more general statement, for certain statements, but not for the ones we are going to do here. So what is the theorem is the following, that the goal, or so, okay, for U chosen at random, and I will say the following holds with probability almost 1. I mean, of course, this can all be made quantitative. I don't want to give you all the details of the parameters, because that's now not useful, but it's exponentially close to 1 in certain parameters. That that the distance of rho prime AR of this maximally mixed state of A prime tensor rho R. So this is the distance between the desired thing and the thing you actually have. Of course, this depends on the unitary. This distance is smaller than epsilon if, okay, maybe it would be better to start with the if above, but okay, I'll write it now like that. If the entropy of A given R of the original state rho is larger than 2k minus n minus plus log, or 2 times log 1 over epsilon. Okay, so what does it tell us? So it tells us that somehow, I mean, this is again a measure of uncertainty. So the larger this is, the more uncertainty does R have about A. So the less correlated they are. So in some way you could say this is a measure of correlation, but it's inverse. So the larger it is, the less correlations you have. Now it says that if the correlations are sufficiently small, in other words, if this measure is sufficiently large. At the moment, you don't need to know what this measure, how it's exactly defined. You just should interpret it as some entropy, some uncertainty. So the fewer correlations you have, the more easy it is to satisfy the criterion. Or you could also say that given a certain amount of correlation, if the k is sufficiently small so that this expression here is smaller than what I have on the left-hand side, then I reach the goal. So the goal, and this thing here, you can ignore that for the moment, this log 1 over epsilon, because it's logarithmic. And because we will usually think of k and n as numbers which are kind of the order of 1,000 or millions, you may ignore that for the moment, just to conceptually understand what's going on. Of course, it's important at the end, because this is a number, but usually let's say, on the scale we look at things, these numbers will be much larger than that. So look at just this thing here. So, and now we can maybe make some examples to understand what it says. Yes? Mm-hmm.
Or let's say for simplicity, like from the set of polymetrics, isn't it that applying a random polymetric?
Okay. This is a. Okay, so this is a very good question. Thanks a lot for asking it, because there is probably a potential ambiguity. So what I mean by that state is the state for one particular u. So you choose u at random, but you know which one. So this is not the average state over all u's.
Or you could equivalently say that you write the description of u into R?
That I could do, yes. Yes. I mean, what I could do is to say, let's add here a u. I mean, I don't now want to do that because that will look at. But the idea is this state is defined for a particular u. And now the statement I make here, which is, I mean, I could maybe here have in brackets u. So this state depends on u. And then the statement that I make here is true for most u's. Yes. But thanks a lot for asking, because that's indeed something I should have said anyway. Yes? Now this is an entropy measure, which I will explain later. For the moment, just think of it as something similar to the von Neumann entropy. The statement is not true if you put here the von Neumann entropy, but it's something, it's the entropy, it's a conditional entropy. So it's somehow how much, I mean, it's somehow, we will see in a certain asymptotic regime, this will be equal to the von Neumann entropy of A given R, which is defined as the von Neumann entropy of rho A R minus the von Neumann entropy of rho R. So it's like a conditional entropy, but it's not that one. The statement is simply not true for the von Neumann entropy in general. But it's true in a certain asymptotic sense when you do it for many repetitions and stuff like that. So now, let me, or there was another question, sorry.
You use randomly chosen U, so uniformly chosen, uniformly distributed. What if you restrict yourself to something which is quite near to the resolution of the system,
Yes.
for example?
This is,
can you do better
yes,
than that?
yes. I will come to that. The answer is yes. We can do much. We can constrain the set from which we choose the U at random enormously. And that's interesting to do because we want at the end to make physical statements. So the bottom line is, yes, we can even take the U from a set that one could claim are only physically possible operations. Of course, the question is what that means. But indeed, it doesn't have to be the harm measured over all possible unitaries. That would be physically irrelevant, I would say. Yes? And this is just fixed. So you just fix that somehow, and the theorem is true however you fix it, because U anyway randomizes stuff. Okay, now maybe two examples, or maybe three small ones. So one example is the case where, so if R is completely uncorrelated to A, and A is completely mixed. So A mixed and uncorrelated to R. Then, I mean, as I said, I didn't formally introduce the measure, but in this case, in all these examples, the entropy is the same as the von Neumann entropy. So in this case, what would be the von Neumann entropy? It would just be n. And this will also be true for this mean entropy, so it's n. So what does it tell us in this case? It means that the whole thing works, so k equal to n still, so goal is achieved for all k smaller equal to n. To n. So essentially for all possible k. And that's clear because if this is already completely mixed, then whatever I do, it will still be completely mixed at the end. I don't certainly introduce any correlations between A and R by doing a random unitaries. And of course a random unitary applied to a completely mixed state will just again result in a completely mixed state. So that's kind of a trivial example. Another extreme case is A fully entangled with R. And in that case, the entropy, I mean, fully entangled, I mean that the marginal state is uniform. In this case, it's again the same as for the von Neumann entropy. You know, for a maximally entangled state, the von Neumann entropy is negative, and it's actually as negative as the number of qubits I have, so it's minus n. So in this case, it doesn't work. So the goal is not achieved for any k larger than 0. And that's also clear because if I'm completely entangled with R, then whatever unitary I do, I will remain completely entangled. And if I have a maximally entangled state and trace out a bit, then this traced out piece will still be completely entangled with R. So this doesn't work. But maybe the most interesting part, which is, however, almost a trivial thing, maybe I write it here, is the part where R, so conditioned on R, A is in a pure state. So in this case, it just means that the entropy is 0. So if the entropy of a pure state is 0, so, and this is also true for the mean entropy. So in that case, this means that the goal is achieved for all k's smaller than n. Of course, it has to be a little bit smaller to incorporate this log 1 over epsilon. And this is a very well-known statement, actually, that follows here as a special case. It means that if you start here with a pure state and do a random unitary and then look at two subsystems, the thing that will happen is most likely, this has been shown by several people before that, for example, Andreas Winter using measure concentration techniques, then these two things will be maximally entangled. But, pardon? Ah, sorry, yes, sure. Thank you. Thanks a lot. So, okay, so again, so the explanation still works. So this will be maximally entangled. Now, if they're maximally entangled, if you look at the smaller system, then the marginal of the smaller system will just be a completely mixed state. And of course, if k is smaller than n over 2, the A prime will be the smaller system. The larger system will also be, I mean, kind of have a rather high entropy, but of course it cannot be, so the entropy of the larger system cannot be larger than the dimension of the small one. This follows from the Schmidt decomposition of the pure state here. But it turns out that most states, so to speak, are maximally entangled. So if you look at the marginal of the smaller system, you will just find a completely mixed state. And this is reproduced by the decoupling theorem. So you see that the decoupling theorem in particular implies these results that are known about these measure concentration or derived from measure concentration techniques. Okay, now I think I'm almost, so we will use that now many times. Let me make one last example which also shows you why this whole thing is connected to thermodynamics. I mean, there will be several connections. So on the one hand, there will be a connection to the problem of thermalization. The other connection will be that it's connected to Landauer's principle. So first I should make the remark that I now already made because of the question that was asked. This statement is still true so I didn't say what chosen at random means. The way it's formulated here, with these exact parameters, is only valid if you choose U uniformly according to the Haar measure from all unitaries. And then you would say, okay, this is not something you have. So in reality, it would be very hard to have such a U. And if you want to apply this in a physical context, it's probably not a useful theorem. But there has been a lot of development. And there's, for example, there has been an increasing understanding of how we can restrict that. And people have looked at, for example, U chosen from what they call a 2 design. A 2 design is a much smaller subclass of all unitaries. And if you choose it from a 2 design, you can still make these statements in almost the same way. You can also choose it from an almost 2 design, which is a still more constrained class of unitaries. It's a smaller class of unitaries, and then you still get the statement with different parameters. And I think the most recent result that I'm aware of is one that you will, if you're going to attend QIP in Barcelona, which will be presented as a talk there by Winton, Brown, and Omar Fuzzy, and Omar was also in Patrick's group, where they showed that if you take the unitary, if you construct the unitary from a random circuit, so instead of looking at just a random unitary, you think here of just some wires, and you have some random gates here at random positions somehow, two-party gates. And of course also gates, they're not restricted to neighboring things, but you take always two wires together and apply a random gate. Then this thing is also true. The parameters are slightly different, but it's essentially still true. And surprisingly, the depth of the circuit has to be only polylogarithmic. I think more precisely, what they showed is that you only need, so the number of gates you need is only n log square n. But n is, of course, already the number of qubits you have. So the depth of the circuit is only O log to the 3n. So with a very short circuit, you can always reach this decoupling. And this is, I think, physically very relevant, because you could now say, if you think of this as a process happening, if the qubits were particles, and if you assume that there are gas that particles randomly meet, then after only that time, log 3n, you have a complete, you have already reached that stage where you could say the system is decoupled. Now, why is this relevant? This is relevant because we will use this process to argue that systems thermalize. So this unitary that I have here will be a model for the process that is actually happening in a physical system when it interacts with a thermal bath. And so let me now give another example. So I already had this example of a coin. I still don't have a coin here. But if I toss a coin, then we usually believe or usually use that mechanism to get randomness. And this is very well explained by this decoupling model. And in some way you could say, if I toss a coin, the outcome of the coin toss is the same as the thermalization of the system. So in using the thermodynamics language, I could say the degree of freedom, whether it's heads or tail, interpreted as a thermodynamic degree of freedom, or as a thermodynamic system, has thermalized. It's now in a uniform state. Both things are equally likely. And that I can understand with decoupling, because what does decoupling tell me? Decoupling tells me I start with a large system. The system is my whole body. I toss this coin, so there are many degrees of freedom, including everything. So I'm doing something typical. So the unitary may, however, be known. So you may exactly know what I'm doing, but the initial conditions are there are lots of degrees of freedom there are. And you may not know everything about the initial conditions when you toss a coin. You may know many things, but not everything, which means that the entropy you have initially the entropy you have before I start tossing the coin is slightly positive. So it's maybe a little bit larger than 0. And now what the decoupling theorem tells you is that typically, for a typical evolution of the coin, even if you know the evolution, that's now referring again to, that's why it's important. So we don't assume we don't use the randomness of the circuit. We just say for a typical evolution, it's now true that if I now only look at 1 degree of freedom, which would be the outcome of the coin toss, which is just 1 bit, then this 1 degree of freedom is most likely completely random and uncorrelated to the knowledge I had. And that's exactly what we want if we toss a coin. But that's also what we want if we talk about the thermalization of a system. So in that sense, the explanation why a coin is random and why a system thermalizes can both be taken as a statement from these type of decoupling theorems. And I call them theorems because, of course, there are different statements depending on what unitaries you consider. But you see there's a very strong connection between the type of problems people look at in quantum information. They study these decoupling theorems, and the type of statements we want to make in thermodynamics, namely whether certain things end up to be random. I now made this coin example, but I will make more thermodynamical examples tomorrow. So the bottom line is that somehow decoupling is a very useful tool to understand processes that appear to be random and to explain why they somehow concentrate randomness. So in some way, what this tells me informally is that if I toss a coin, then all the randomness or all the uncertainty you have in the initial conditions is somehow concentrated into the single degree of freedom of the outcome of the coin toss. Concentrated sounds maybe stronger than it is, but the point is I can, of course, take any small degree of freedom and the statement will be true. Okay, yes? Yes, that's a good question. So in principle, when I talk about coin tossing, I could now take a classical perspective where I say all knowledge about my initial condition, about the initial conditions you have, is classical. And in this case, you could apply the theorem without R and just model this as the state you have initially. Now, more generally thinking, and of course in thermodynamics this will be relevant, maybe for coin tossing you never have quantum knowledge about me, but in general you may of course be in a situation where you carry a system that is somehow entangled with the coin initially, or with me. Let's say we have met and now we are entangled. So now the question is, can you still make such statements? And the answer is yes. And now, because there is entanglement, you can no longer translate the statement into a statement where you condition on R, because you cannot condition on a quantum system. So in other words, the short answer is, as long as your knowledge about the system is purely classical, then I don't need the system R. But the theorem is more general. It even applies to knowledge that is itself quantum mechanical. And that's important because the reference will not necessarily be, in thermodynamics, a person with knowledge. In thermodynamics, the reference could just be an environment. And the environment can, of course, be correlated or quantum correlated to the system. And in order to be able to apply the decoupling statements, we need this system R. But if you would think completely classic, if you only want to analyze a classical coin, you wouldn't want to do it. By the way, if you only analyze a classical coin, you may also want to restrict this thing not to unitaries, but to purely classical operations, maybe. And that would result in a slightly different statement. And then it's actually a statement which is very similar to privacy amplification or randomness extraction. So in some way, you could see this decoupling mechanism as a quantum version of what you do for those who are familiar with randomness extraction, which also says that if you have some uncertainty about the input, then one individual bit of the outcome will be completely random. Yes?
So the type of random circuit that Brown and Fowler consider is like a time-dependent Hamiltonian that's consulting a lot of randomness during the course of the evolution. But when we think of thermalization of physical systems, normally we imagine there's some time-independent, chaotic Hamiltonian which achieves the decoupling.
I would say, I mean, this is, again, so the theorem is true for a fixed, so for each fixed unitary, it's, so in some way, in this expression, there's a fixed unitary, so you don't make use of the randomness.
But the point is we want to consider some, well, right, but I mean, so you're making the, I guess you're not really making the claim, but you're suggesting that we are gaining a deeper understanding of thermalization and quantum statistical mechanics from the decoupling theorem, which I guess I would like to believe is true. But we don't really get what we want by considering these ensembles of unitaries which consult a large amount of random.
So the way I see it, I mean, this is an important point, but I think one way to see that, or at least the way I interpret it is the following. So I don't see that thing as randomness of the same type as the randomness we get at the end. I see it more like that. So you could say like, if this is the space of all unitaries, and here is maybe the single unitary that is actually happening in reality. So let's say there is no there's no randomness coming in. I don't want to bring in randomness via the unitary. So there's one single one here. Now we have a statement that applies here to, first of all, the first version was it applies to most unitaries. Now if you are unlucky, these most unitaries are all those and don't include the one we actually have. Now the newer statements restrict somehow the set to, we certainly know somehow that the unitary that is here is in a smaller set of unitaries that maybe consists of local interactions. Now, if we now have a statement saying that for most unitaries in this small set, it's true, then it's somehow more likely that the actual unitary we have is there. By more likely, of course, we don't know where that is, but we can be more confident that the small, we want, in some way, the goal of all this research should be to, at the end, only have a statement about the actual unitary we have. And I think we will never be that far because we even don't know what's the unitary.
I'm not asking for that much, but there are two different ensembles we can consider. One is an ensemble of unitaries we can get by evolving with respect to some local, time-independent Hamiltonians for a finite amount of time.
Yes.
And the other is an ensemble like random circuits or two designs.
Yes.
And we'd like to make some connection.
But I would really like to see it as something time-independent. So I think of it as really there's one fixed unitary. And unfortunately, we can never make a statement about that one fixed unitary. What we can make instead is a statement about an as small as possible set of unitaries that includes the one we are interested in. And then it's just a matter, this is now not strict, but we hope now if the set is small enough from which we choose, at the end we have a statement that for most unitaries in this set it's true. If the set is very small and we have a statement that is true for most of them, then we could hope that the one that is actually happening, which is a time independent now, is included in our statement.
But we have no such statement yet, right?
No, we make somehow this set smaller and smaller. And it's true, I would not be, I don't believe that we can ever make, of course, ideally, our set of unitaries should be this single, only contain this single element of the actual unitary that is happening. I don't think we will ever be able to reach up, in particular because we don't have a good description of what this unitary is. But what we can hope for is to make the set which is still required. So it's still a weaker statement we want than we would ideally want. But if this set is very small, you have kind of a good approximation in some way of the physical situation. So I don't want to think of like this unitary is chosen at random. I don't like that because that brings it in additional randomness. I really see it as a fixed unitary, but because of technical reasons, we are not able to prove something for this fixed unitary, so we try to approximate the unitary we have by doing so. So it's somehow similar to like people considering, let's say, statements for certain types of states, like they look at PEP states and so on, because it's more likely, like if you have a statement that is true for most PEP states, it's more likely that the actual physical state you have, which is just one state, there's no randomness, is covered by the theorem. So of course I could be always unlucky, and even if I make this set small, the actual unitary that is happening in physics is just not in, if I make this almost statement, that it's true for almost all, that I'm very unlucky and the actual unitary that is happening in reality is never included in that. But then I'm just unlucky in some way. But I could also hope that in some way not all physical processes are just that badly designed by God that they always evade my proof. But you're right. We will never have that statement. I can just, I think, but it's always in advance. So the smaller this set is, and as long as we can still prove that with probability almost 1 within this set, it's, or that, I shouldn't talk about probability, that something is true for almost all elements of the set, and the set is already very small, then I think we are closer and closer to the statement we would like to have, which we will probably never reach, but we would like to have. I hope this answers partially your question. Okay, I think time is now over. Next time I will use this decoupling theorem to prove this statement that I promised. The statement is that we can say something about how much work it costs to actually implement a physical process. There's a question, yes?
It's a bit of a crazy question.
Okay.
Supposing I have a classical pack of cards, a standard pack of cards, and I shuffle.
Yes.
You can say that you'd increase the
Yes.
entropy if you take an ensemble of
Yes.
pack of cards.
Yes.
Could you do the same thing with a quantum pack of cards and you do a unitary transformation instead and say something that relates the two scenarios?
Yes, I think this is a question of that type. The question would now, of course, be how do you model the unitary that corresponds to shuffling cards? But if you have a good model for these unit, like...
I want to compare the two, the classical versus
Aha.
the quantum, and say the quantum somehow
is better.
mixes things more.
Yes, I mean, that at least happens in this case. As you can see here, even if the entropy is 0, so classically you wouldn't gain any... I mean, clearly if the entropy initially is 0, you wouldn't expect to have any randomness after a classical mixing at the outcome. However, in the if you have a unitary, even if the entropy is 0, you can still use half of the system and have a lot of randomness. So in that sense, yes, the answer would be that one would expect that if you have unitaries, they mix much better than classical randomness. Classical mixing, yes. Okay. So then I would like to end this lecture. Thanks for your attention.